Welcome! In this session, we'll dive into problem number 552, Student Attendance Record 2. This problem challenges us to explore different algorithms for counting attendance records that meet specific criteria. Get ready to enhance your problem-solving skills and deepen your understanding of dynamic programming. In this problem, we are tasked with evaluating a student's attendance record for a given number of days, denoted by the integer n. Each day in the record is represented by a character, which can either be a for absent, L for late, or P for present. The goal is to determine the number of valid attendance records of length n, where a record is considered valid if it satisfies two specific criteria. First, the student cannot be absent for more than 1 day in total. Second, the student cannot be late for 3 or more consecutive days. Since the result can become very large, the number of valid records should be returned modulo 10 to the power of 9 plus 7. The input is a single integer n, ranging from 1 to 10,000, and the output is the count of valid attendance records conforming to these rules. The output of the problem is a single integer representing the number of valid attendance records modulo 10 to the power of 9 plus 7. Let's consider a simple example where n is equal to 2. For this case, there are 8 possible attendance records: PP, PL, LP, LL, AP, PA, AL, and LA. None of these records violate the given rules, as no record contains more than 1 or 3 consecutive Ls. Therefore, the output for this example is 8. This demonstrates how all combinations of length 2 that meet the criteria are counted. Now, looking at another example where n is 1, the possible attendance records are much simpler. With a length of 1, the only valid records are P, L, and A, since no rule violations can occur with a single day. This gives us a total of 3 valid records, so the output in this case is 3. This example highlights how the constraints naturally limit the possibilities when the input size is small. For a slightly larger example where n is 3, the number of valid records grows significantly. For n equal to 3, there are 19 valid attendance records. These include records without any A, such as PPP, PPL, PLP, PLL, LPP, LPL, and LLP. Additionally, we have records with exactly 1 A, like AP, PAP, PPA, ALP, PAL, LAP, PLA, LLA, and all. Each of these combinations adheres to the rules, avoiding more than 1 absence and ensuring there are no sequences of 3 or more consecutive Ls. The total count of valid records for this input size is 19, demonstrating how the number of possibilities grows as n increases. To handle all inputs efficiently, we need to consider a few edge cases. For the minimum input, when n equals 1, the only valid records are P, L, and A, all of which are valid by default. For the maximum input of 10,000 days, the solution must be optimized to compute the result without exceeding time or memory constraints. Additionally, care must be taken to exclude records that contain invalid patterns, such as 3 consecutive Ls, for example, LLL, or records with multiple As, like AAP or PAP. These edge cases ensure that the solution is both robust and efficient, covering the full range of possible inputs. To solve this problem, we first consider the brute force approach. Here, we generate all possible attendance records of length n using the characters A, L, and P. The goal is to count the strings that satisfy the conditions: there can be no more than 1 A, and no 3 consecutive Ls. While this method is intuitive and straightforward, it comes with a significant drawback. The total number of possible strings grows exponentially as 3 to the power of n, leading to an impractical time complexity of 3 to the power of n, for larger values of n. This makes the brute force approach computationally infeasible. To address this, we turn to dynamic programming. Instead of generating all strings, we break the problem down into smaller, manageable subproblems. The key insight is to define a state, represented as dp, I, A, L, where I is the length of the attendance record, A is the count of A's used so far, either 0 or 1, and L is the count of consecutive L's at the end of the record, ranging from 0 to 2. This state-based approach allows us to systematically build solutions for larger n by leveraging solutions for smaller n. Using dynamic programming, we define transitions to calculate the next state based on the current one. First, to add P, we update dp, I, A, 0, by summing over all valid dp, I1, A, J states, where J represents the different counts of consecutive Ls in the previous record. Next, to add we update dp I10 by summing over dp I10 j states, but only if the current record has no a yet, ensuring the constraint of at most one is satisfied. Finally, we handle L by updating dp I a L using dp I1 a L1, provided L is 1 or 2. This systematic updating ensures we only count valid records. Once all transitions are processed, the result is obtained by summing all valid dp n a L states, covering all allowable combinations of a and L. This reduces the time complexity to O, n, making it much more efficient than brute force. Additionally, we can optimize further by reducing space complexity. Instead of maintaining a full dp table, we only keep track of the previous state, allowing us to compute the current state and discard earlier ones. This reduces space usage from O, n, to O, 1, while maintaining the same correctness and efficiency. The dynamic programming approach is chosen for its balance of efficiency and clarity. It eliminates the exponential growth of the brute force method and ensures we only compute valid states, adhering to the problem's constraints. The key realization is that any valid attendance record of length n can be constructed by appending p, l, or a to a valid record of length n1. By tracking the number of A's and consecutive L's as part of the state, we ensure no invalid records are counted. These constraints significantly reduce the state space, making the problem tractable. When comparing approaches, brute force, though simple, becomes infeasible for large n due to its O, 3 to the power of n, complexity. Dynamic programming, on the other hand, achieves an ideal time complexity of O, n, making it suitable for n up to 10,000. The space-optimized version further enhances scalability by reducing memory usage to O, 1. For this reason, the space-optimized DP approach is the final choice. It efficiently handles large inputs while maintaining clarity, correctness, and adherence to the problem's constraints. The problem we're addressing involves finding the number of valid attendance records of a given length n. These records must meet two key conditions: they can have at most one A, which stands for absent, and they cannot contain 3 consecutive L, which stands for late. To start, we can approach this problem with a brute force method. This involves generating all possible attendance records of length n using the 3 possible characters, A, L, and P, where P stands for present. The total number of combinations for strings of length n is 3*n, since there are 3 choices for each position. For example, if n is 2, the possible strings are AA, AL, AP, LA, LL, LP, PA, PL, PP. This gives us a complete set of potential attendance records to work with. Once all the possible strings are generated, the next step is to filter out the invalid ones. For each string, we check its validity by applying the given conditions. First, we count the number of A characters. If there is more than one A, the string is deemed invalid. Next, we search for the substring LLL. If it appears, the string is also invalid. Tools like the count function for A and substring matching for LLL make these checks straightforward. After identifying the valid strings, we keep a counter to track how many there are. For instance, with n equals 2, the valid strings are AP, PL, PP, PA, LP, giving us a total of 5 valid records. Finally, we return this count as the result of the brute force approach. While the brute force method is conceptually simple, it is computationally expensive. The inefficiency arises from the exponential growth of combinations, 3*n, which becomes impractical for larger values of n. However, the problem's constraints provide opportunities for optimization. For example, we can prune invalid strings early by enforcing the conditions during generation, which avoids unnecessary computation. Additionally, instead of generating all strings explicitly, a dynamic programming approach offers a more efficient solution. In this approach, we build valid strings incrementally, keeping track of states based on the number of A used and the consecutive L count. By defining clear state transitions and avoiding redundant computations, we can significantly reduce the time complexity. Now, let's analyze the time and space complexity of the brute force approach. Generating all strings requires O, 3 to the power of n, operations, and validating each string involves counting and searching for LLL, which takes O, n, for each string. Therefore, the total time complexity is O, 3 to the power of n*n. For space complexity, storing all the strings requires O, 3 to the power of n, space. To better understand this, consider an example where n equals 2. The generated strings are AA, AL, AP, LA, LL, LP, PA, PL, PP. Each string is validated. AA is invalid due to 2 A's, while the rest are valid. This gives us 8 valid strings out of the 9 generated. The inefficiency of this method highlights the need for more scalable solutions. Finally, the output for our example with n equals 2 is 5, as there are 5 valid attendance records that satisfy the given constraints. This result demonstrates the correctness of the brute force approach for small values of n, but also underscores its limitations in handling larger inputs due to its exponential time and space complexity. Moving forward, we can explore dynamic programming and optimization techniques to address these challenges more efficiently. This Python implementation solves LeetCode problem number 552, student attendance record 2, using dynamic programming. The goal is to count all valid attendance records of length n where there can be at most 1 A, absent, and no 3 consecutive L, late. The function begins by defining the modulus mod equals 10 to the power of 9 plus 7 to ensure results fit within integer limits. We handle small cases explicitly. If n is 0, the result is 0. If n is 1, there are 3 valid records, P, L, and A. Next, we initialize 2 DP arrays. DP tracks valid records with at most 1 A, while DP_no_A is for records with no A. Base cases are set for both arrays at n equals 0 and n equals 1. The core logic iterates from I equals 2 to n. For DP_no_A, I, we calculate valid records ending in P, L, or LL by summing values from previous indices. For DP, I, which includes 1 A, we add contributions from both DP_no_A and earlier values of DP, allowing 1 A before the current position. The modulus ensures all calculations remain efficient. Finally, the result DP, n, is returned. This approach has a time complexity of O, n, due to the loop, and a space complexity of O, n, for the DP arrays. Here, we begin by defining the method checkRecord, which takes an integer n representing the length of the attendance record. We also define a constant mod to handle large numbers and ensure our calculations remain within the limits of integer values. Next, we include base cases. If n is 0, there are no valid attendance records, so we return 0. If n is 1, there are 3 valid records, P, L, and A, so we return 3. Now, we initialize 2 dynamic programming arrays, DP to store the total number of valid sequences up to length I, and DP_no_A to store the valid sequences up to length I that do not contain the letter A. For DP_no_A, we initialize DP_no_A 0 to 1, representing a sequence with only P, and DP_no_A 1 to 2, which includes P and L. Similarly, for DP, DP0 is initialized to 1, and DP1 is set to 3 to account for P, L, and A. We then use a loop to calculate the values for DP_no_A and DP for all lengths from 2 up to n. For DP_no_A, I, we add the values of DP_no_A, I1, DP_no_A, I2, and DP_no_A, I3, to account for appending P, L, or LL to sequences that already exclude A. Each step involves taking the modulo operation with mod to ensure our results stay within bounds. For the DP, I, calculation, we add the value of DP_no_A, I, to represent sequences of length I that do not contain A. Additionally, we include DP, I1, DP, I2, and DP, I3, to account for sequences where A is inserted at different positions. Again, we use the modulo operation to keep numbers manageable. This loop continues until we compute all values up to n. Finally, we return DP, n, which represents the total number of valid attendance records of length n under the given constraints. This implementation efficiently uses dynamic programming to solve the problem within the constraints and ensures correctness by carefully handling edge cases and large numbers using modular arithmetic. This problem, student attendance record 2, requires us to calculate the number of rewardable attendance records of a given length n. A rewardable record must contain at most 1 of 4 absent and cannot have more than 2 consecutive else 4 late. To solve this efficiently, we use dynamic programming to count the valid attendance records. For example, when n equals 2, we initialize the DP_no_A array, which tracks valid strings with no A. For a string of length 0, there's only one valid empty string, so DP_no_A 0 is 1. For a string of length 1, the valid strings are p and l, so dp underscore no underscore a, 1, equals 2. Similarly, we initialize the dp array, which tracks all valid strings, including those with 1a. At length 0, there's still just the empty string, so dp, 0, equals 1. At length 1, we include p, l, and a, giving dp, 1, a value of 3. To calculate the values for n equals 2, we first determine dp underscore no underscore a, 2, the number of valid strings of length 2 with noa. By appending p to valid strings of length 1, we add 2 to dp underscore no underscore a, 2. By appending l to valid strings of length 0, we add 1 more. This gives us a total of 3 valid strings, pp, pl, and lp. Next, we calculate dp, 2, which includes all valid strings of length 2, even those with 1a. We start by adding dp underscore no underscore a, 2, which contributes 3 strings with noa. Then, we append it to all valid strings of length 1, contributing another 3 strings. This gives a total of 6 valid strings of length 2, pp, pl, lp, ap, al, and pa. Thus, dp, 2, equals 6. Now, let's extend this to n equals 3. We initialize dp underscore no underscore a and dp as before, with dp underscore no underscore a, 0, equal to 1, dp underscore no underscore a, 1, equal to 2, dp, 0, equal to 1, and dp, 1, equal to 3. The calculations for dp underscore no underscore a, 2, and dp, 2, remain the same, giving values of 3 and 6, respectively. For dp underscore no underscore a, 3, we start by appending p to valid strings of length 2, adding 3 strings. Then, appending l to valid strings of length 1 adds another 2 strings, and appending ll to valid strings of length 0 adds 1 more. This gives a total of 6 strings, ppp, ppl, plp, lpp, pll, and llp. To compute dp, 3, we first add dp underscore no underscore a, 3, contributing 6 no-a strings. Then we append it to valid strings of length 2, adding another 6. Finally, inserting it into the middle of valid strings of length 1 adds 3 more. In total, dp, 3, equals 15, with examples like ppp, ppl, plp, pal, ap, and lpa. With n equal to 4, we begin with the same initial values, dp underscore no underscore a, 0, equals 1, dp underscore no underscore a, 1, equals 2, dp underscore no underscore a, 2, equals 3, and dp underscore no underscore a, 3, equals 6. To find dp underscore no underscore a, 4, we append p to valid strings of length 3, adding 6 strings. Appending l to valid strings of length 2 adds 3 more, and appending ll to valid strings of length 1 adds 2. This gives a total of 11 valid strings with noa. For dp, 4, we start with dp underscore no underscore a, 4, contributing 11 no-a strings. Adding it to valid strings of length 3 gives 15 strings, and inserting it into the middle of valid strings of length 2 adds 6 more. This results in a total of 32 valid strings of length 4, such as ppp, pppl, plpp, plp, appl, and many others. At this stage, we conclude that for n equal to 4, the total number of rewardable attendance records is 32, as determined by dp, 4. This dynamic programming approach efficiently calculates the number of valid strings by building on previously computed results, ensuring that we handle the constraints of at most 1 and no more than 2 consecutive Ls. By using modular arithmetic, we also ensure that our results remain within the required bounds, making this solution both optimal and scalable for larger values of n. The time complexity of this solution can be broken down into 3 main parts. First, initializing the dp and dp underscore no underscore a arrays. Since these arrays each have a size of n plus 1, filling them up initially is an O(n) operation. Next, in the main loop, we iterate from I equals 2 to n, meaning the loop runs n 1 times, which is O(n) in terms of complexity. Within each iteration, the calculations for dp underscore no underscore a, I, involve 3 additions and modulo operations, all of which are O(1). Similarly, updating dp, I, involves up to 4 constant time computations. Since these operations are O(1) per iteration, the total cost of the loop is O(n). Lastly, the return statement simply retrieves the value of dp, n, which is an O(1) operation. Combining these, the overall time complexity includes O(n) for for initialization, O(n) for the loop, and O(1) for the return, giving us a total time complexity of O(n). Now that we've established the time complexity, let's summarize it. The initialization step is O(n), the loop is O(n), and the final return is O(1). Adding these together, the total time complexity remains O(n). Next, we look at the space complexity. The two primary contributors are the arrays dp and dp_no_a. Since each of these arrays has a size of n+1, the total space required for them is O(n). Additionally, we use a few auxiliary variables, such as mod and loop indices, which collectively require constant space, or O(1). Since the arrays dominate the space usage, the overall space complexity is O(n). To summarize the total space complexity, it is O(n), driven by the space required for the dp and dp_no_a arrays. Now, let's analyze the best, average, and worst-case scenarios. Unlike some algorithms where the complexity can vary depending on the input, this solution consistently processes all n states linearly, regardless of the input. This means the time and space complexities are always O(n), with no differences between best, average, or worst cases. The algorithm's performance remains predictable and efficient for all inputs, making it highly reliable. It's helpful to compare this dynamic programming approach with a brute force method. A brute force approach would generate all possible attendance records of length n, which amounts to 3 to the power of n possibilities since each position can independently be p, l, or a. For each record, we would also need to check its validity, which takes time. This results in an overall time complexity of n*3 to the power of n for the brute force solution. By contrast, our dynamic programming approach reduces this significantly to n. It does so by avoiding redundant computations and leveraging the overlapping subproblems inherent in the structure of the problem. This comparison highlights the immense efficiency gained through dynamic programming. To solidify our understanding, let's provide a mathematical justification for the big O complexities. For time complexity, the loop iterates O(n) times, with each iteration performing O(1) work. This gives a total time complexity of O(n). For space complexity, the primary contributors are the arrays dp and dp_no_a, each of size O(n). These dominate the overall space usage, leading to a space complexity of O(n). In conclusion, this algorithm is optimal for solving the problem, reducing the exponential complexity of brute force to linear time and space. This makes it both efficient and scalable for larger inputs. One common mistake when solving this problem is not accounting for edge cases, such as when n equals 0 or 1. These cases can produce unexpected behavior, like empty strings or single-character strings, which must still be evaluated. To address this, it's essential to explicitly check for these small input sizes and handle them appropriately in your code. Another frequent issue is misinterpreting the problem constraints. For example, you might overlook the condition that there can be no more than one in the record or misunderstand what qualifies as a valid record. The best way to avoid this pitfall is to carefully read and reread the problem statement and constraints to ensure you fully understand them before starting implementation. Lastly, relying on a brute force approach for large values of n can lead to inefficiencies. Generating all possible attendance records has exponential time complexity, which quickly becomes impractical. Instead, dynamic programming can be used to break the problem into smaller, manageable subproblems and significantly optimize the solution. Another common error arises from incorrect state transitions in dynamic programming. If you mismanage how states transition, such as forgetting to enforce the condition that only one is allowed, it can corrupt your intermediate results. To avoid this, it's crucial to clearly define the states and their transitions before coding, using a table or diagram to map out the logic. Additionally, failing to modularize results when working with large outputs can cause overflow errors. When the problem specifies returning the result modulo a large number, such as 10 to the power of 9 plus 7, this aspect cannot be ignored. The solution is to consistently apply modular arithmetic throughout your computations, whether you're working recursively or iteratively. This problem serves as an excellent example of state-based dynamic programming, where multiple constraints, like the count of a and consecutive L, need to be tracked. Understanding how to handle these constraints is a valuable skill that will help you tackle other dynamic programming problems with similar structures. In interviews, it's important to articulate the trade-offs between approaches. For instance, you can explain why brute force fails for large inputs due to its inefficiency, and how dynamic programming addresses this with better performance. Space complexity is another key area interviewers might focus on. Discuss how you can reduce space usage from O(n) to O(1) by storing only the last few states. Breaking down the problem into subproblems and defining the recurrence relations is another skill you should showcase. Related problems that can help you practice similar concepts include LeetCode 70, which focuses on valid paths and a staircase problem, and LeetCode 91, which requires careful handling of constraints in decoding ways. Other good examples are LeetCode 139, which tracks valid states for word breaks, and LeetCode 376, which focuses on state transitions in a wiggle subsequence. There are several approaches to solving this problem, each with its own trade-offs. Brute force is the simplest to implement but comes with exponential time complexity, making it suitable only for very small values of n. It can still be useful for validating or debugging optimized solutions. Dynamic programming, whether implemented in a top-down recursive style or a bottom-up iterative style, is a more efficient approach. The top-down method is intuitive but can lead to stack overflow or redundant calculations unless memoization is used. Bottom-up dynamic programming, on the other hand, is efficient in both time and space but requires careful setup of states and transitions. Finally, space-optimized dynamic programming is a great option when you need to reduce space usage from O(n) to O(1). While it requires a more complex implementation, this approach is an excellent way to demonstrate optimization skills, especially in follow-up discussions. Great work! To summarize, we tackled problem number 552, explored a dynamic programming approach, and analyzed its efficiency. Keep practicing and refining your skills. Thanks for watching, and stay tuned for more problem-solving tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!